Hi, I'd like to share the answer to the problem that I asked you to do. And this problem involved four standard solutions that you had the concentrations according to the calculations that you did with dilution using the stock solution that we had. And I had specified stock solution of 0.350 molarity. And then we went ahead and calculated the four concentrations of the standard solutions. And then we took those solutions, took it to a spectrophotometer and measured the absorbances for those solutions. And I asked you to prepare a Beer's law plot for these four solutions. This is called Beer's law plot for the Beer's law standard solution plot. And I gave you two problems. And these involved giving you an unknown solution. One was unknown A, and we wanted to use the Beer's law plot equation to calculate the concentration in molarity of solution A, and Beer's law plot to calculate the concentration of solution B. And I want to share with you, I ask you to prepare an Excel spreadsheet of the problem and do your plot and calculate the A and B. And I want to share with you my Excel spreadsheet so you can compare answers and see if you did it correctly. So here is the spreadsheet that I prepared for the problem. And so I essentially just plotted or just typed in the values for solution 1, 2, 3, 4. And for solution 1, for example, I put in 0.035 molarity and absorbance was 0.0150. I also adjusted the formatting for these values so they represent the sig fig of the problem. And it's a good practice to do whenever you're presenting data. And then next thing I did is I prepared the plot, standard Beer's law plot of the video example I gave you. And when I plotted it, I plotted the absorbance on the y-axis and concentration on the x-axis. And I also, as you see, I adjusted the formatting of the x and y values. So for the y values, I went with a 4 decimal, a number format with 4 decimal places to show a 3 sig fig absorbance values. And I also did the same for concentration. But it's hard to fix on Excel, but essentially like when you go past the 0.08 mark, these zeros really are not significant. But you can't really do anything about it on Excel. You just have to accept it. But know that if you're predicting values for the ranges shown, you have to limit yourself to the precision of the value that you found based on the experiments. So important features of the plot is that we made sure that the line goes through 0, 0, even though Excel doesn't show it. There is no intercept here. It's just y equals mx. And Excel does report a slope of 0.4338, and the R-squared value is 1. It's not exactly 1, I'll show you. And so I found the information that Excel gave me in terms of the slope. This is the important information. And I actually typed it in so as an equation. And this is an equation that I had given you before. So this is equal to line est. Line est is a function on Excel that allows you to set the intercept to 0. So you show your y values and your x values, comma, and then you put a 0. That means pass the line through 0, 0. So line est is the slope value. And I just put it up here so you can see it right over here is the equation for it, where it shows the function at line est. And then it's, so I started actually with equal sign and I just put the at there for me. And it's G5, G8 is the range of the y values, G5 through G8, and then F5 through F8, comma 0. And notice what it did. It gave me the slope value to more digits of precision that I need. That's just so that I won't have any round off error. I could have taken the 0.4338 from the graph, but sometimes the sig fig of what they report to you on the graph, it may not be the proper sig fig. It may be lower. In this case, it's not. And sometimes you don't maybe necessarily want to graph something to use the slope. So I also calculated the R-squared value. It's not really 1 as the graph shows exactly 1, but it's pretty close to 1. And that's because I made this data up and I made it to where the points follow the straight line really well. I just made slight modification that it is not giving me 100% correlation, but it's very close. So anyway, now remember the point A and B, you're trying to calculate the concentrations. Absorbances were given to you, so these two values were given. This one and this were given in the problem. And so these two cells are calculations. So I want to just point to that cell and look at the formula on the formula bar and see how it's done. This formula bar is shown here on that corner. Fx equals, that's the formula, G9 divided by F2. G9 is my absorbance for point A, unknown A, divided by F2. And F2 is my value for the slope. That's the calculated value. The same exact calculation is done with the other cell for unknown B. And so you have those concentrations. So concentration of unknown A, let's call it C, concentration of A is equal to 0.116 molarity in correct sig fig. Concentration of unknown B is equal to 0.0576 molarity. And this correlates with the sig fig of my graph that's within these ranges. Now, the advantage of Excel obviously is using the equation. And in the old days when people had to plot by hand, they had to essentially read from the graph. Of course, you could always get the equation of the line when you plot by hand, but the logic of it is still good for you to follow. When your absorbance is for concentration A, for solution unknown A, is 0.0505, it's sort of like right over here somewhere. So, I'm sorry, I'm good looking at the concentration. So absorbance is 0.0505, so it'd be like right over here. So notice that if you have an unknown absorbance of 0.0505, using the equation is same thing as going to the line and reading this concentration. So this is what you read from the graph. Again, we don't read it, we use the equation, but the logic of it is good for you to know because, and I stress this, that you do not want to be plotting A and B. A and B are unknown solutions. I already plotted my 4 standard concentrations, 1 through 4. 4 being is the most concentrated, so this is my solution 4, solution 3, solution 2, and solution 1. And those are solutions that I prepared from my stock solution. And everything else, if I'm given any other unknown, no matter where it is, in terms of concentration, as long as I'm below the 0.14, I can trust the data to be nice and linear. If you go beyond 0.4, you can be sure if that data is linear, because sometimes when it gets more concentrated, the equipment response sort of levels off like this. And that's when you run into nonlinearity and your prediction is not going to be good. So we don't want to go beyond a maximum of 0.14 for concentration and 0.0600 for absorbance. Anyway, I wanted you to check your answer and see the spreadsheet the way I prepared it and perhaps the way you prepared it, and see what advantages I presented in terms of using the equation for the slope as line S, and just that. So I hope you've gotten the principle of spectrophotometry. This is the basic idea demonstrated through this example. That's it.